Hi, first of all, thank you for showing an interest in my work. My name is Gerald Drenten, and I will talk about optimal B-value sampling for interstitial fluid estimation using IVIM. I have nothing to disclose. I will start with a short introduction. IVIM, or intravoxel incoherent motion, is a diffusion-weighted MR technique with a range of B-values. It has the potential to simultaneously measure the parenchymal diffusion and microvascular perfusion. When looking at the MR signal with respect to relatively high B-values, we observe that the signal decays exponentially. However, the signal for lower B-values do not follow this relation due to the presence of an additional perfusion-related component. This is referred to as the IVIM effect, and from this the perfusion signal fraction can be calculated. Traditionally, the diffusion and perfusion components are separated using bi-exponential models. But recently, spectral analysis, such as non-negative least squares, gained attention. The non-negative least squares provides a spectrum of IVIM components for each voxel. For example, the spectrum for a specific voxel might look like this, with a microvascular perfusion and a parenchymal diffusion component. From this, the perfusion fraction can be calculated. Looking at a different voxel, placed in the white matter lesion, we might find an additional component, dubbed the intermediate component. Similar to the perfusion fraction, we can calculate the intermediate fraction. Doing this for all voxels results in an intermediate fraction map, as shown here. The intermediate fraction might be related to interstitial fluid in enlarged perivascular spaces and white matter lesions. These type of lesions are associated with a number of disorders, ranging from Alzheimer's disease to stroke and multiple sclerosis. Therefore, estimating the intermediate fraction from IVIM data can provide valuable insights. Previous research has already shown the effect of different B-value sampling strategies on the estimation of IVIM metrics. However, the effect on the intermediate component has not yet been studied. Therefore, in this study, we will determine the optimal B-value sampling for estimating the intermediate component. We used a genetic algorithm to calculate the optimal B-values. First, a population is randomly initialized and it is described as binary vectors with 15 non-zero elements representing the B-values. Subsequently, the performance of each strategy is determined using the so-called fitness function. Here it is represented as the root mean square error of the intermediate component fraction. Next, the best performing strategies will be selected, and using crossover and mutations, a new population will be created. This is then the second generation, and this process is repeated until the 250th generation. In the figure on the right, the evolution of the best performing B-value sampling is shown over the generations. It can be seen that the algorithm converges after about 100 generations. To make sure that the B-value sampling is not driven by the random initialization of the first generation, the process is repeated for multiple times to obtain a distribution of optimal B-values. And from this, we can define the optimal B-values, shown in green on the slide. The performance of the optimal B-value sampling is assessed with respect to a linear and logarithmic sampling, using simulated data. For these simulations, a high SNR case was considered, mimicking region-wise fitting. The performance of each sampling strategy was assessed in terms of the root mean squared error. The figure on the right shows the error plots with respect to the ground truth. A for the linear, B for the logarithmic, and C for the optimal sampling. And it can be clearly seen that the optimal sampling best approaches the ground truth. Furthermore, this can be seen from the root mean square error, which is about 2.9 times lower for the optimal case compared to linear and logarithmic. Three-component fitting of exponential decays is a difficult problem, and it depends on the acquired B-values. In this study, we showed that the diffusion component related to interstitial fluid can be quantified more accurately by using dedicated sampling schemes aimed at this specific component. Thank you for your attention. If you have any questions regarding this work, I would be happy to answer them.